compact, super-energetic particles filled each minute drop of space-time. As a drop stretched and cooled, its particles began to lose their energy. The mysterious property known as mass had not yet come into being. 1/100th of a billionth of a second after the Big Bang, when the temperature had dropped a fraction, something strange began to happen. The entire universe seems to have become permeated with a field or presence that dramatically materialized in a similar way that steadily cooling water suddenly turns to ice. This phase change into what is now known as the Higgs Field appears to have had a remarkable effect on the elementary particles that had previously been whizzing about at the speed of light. Some particles travel through the Higgs field virtually unimpeded, but other types of particles were dragged to slower velocities by varying amounts. It was as if the Higgs field was acting as a kind of selective treacle. The more the particles were slowed by the Higgs field, the more of their energy has been condensed into a super-concentrated form of energy known as mass. Einstein showed that energy and mass were interconvertible. Energy can become mass, and mass convert back to energy. The Higgs field appears to share these two manifestations differently for our four particles. The electron is mainly energy, the muon a bit more mass, the W particle more still, and the top quark is nearly all mass and very little energy. But how can this Higgs field confer mass on a particle? In the quantum mechanical world, fields such as the Higgs field are envisaged as being made up of many tiny particles. These messenger particles that convey the effects of such fields are known as bosons. In this case, they'd be Higgs bosons. On closer inspection, the Higgs field is far from static. Its fluctuating levels are represented by Higgs bosons coming into and out of existence. The result is a boiling sea of jostling particles. Now, when our electron enters this field, it slips past the Higgs particles with ease. The muon, being less slippery, encounters more friction with the Higgs field. The W particle makes quite heavy weather of its passage, with the Higgs particles getting quite a purchase on it and slowing it down considerably. Finally, the top quark locks readily with the Higgs bosons and is slowed down greatly, converting much of its kinetic energy into mass. If this hypothesis is correct, and Higgs bosons do come into and out of existence, theoretical physicists believe it should be possible for experimenters to create and destroy Higgs bosons. And that is one of the primary missions of CERN's Large Hadron Collider. Theoreticians predict that the energy exchanged in a direct collision between two protons travelling at nearly the speed of light in the Large Hadron Collider should force the creation of a Higgs boson. An exact head-on collision of two protons is rare, but that is still not accurate enough. It's getting a direct hit between ingredients of each proton that could create a Higgs boson. Chances of such a collision are low, but if enough are generated, CERN hopes that such events will occur and, like roadside speed cameras, will flash the Higgs for all the world to marvel at. Physicists suggest that if there is a Higgs boson, it will immediately disintegrate into other recognizable particle pairs, and it's the presence of these smoking guns that will finally indicate that the Higgs boson is more than a figment of theoreticians' minds, and CERN will have revealed yet another major building block of our understanding